And then we move on to our next speaker, who is Claudia Ratti from Texas. And
yes.
she will...
Hi.
Hello. Wonderful, that works. Okay, so we will get an overview of the best collaboration and Lattice QCD results. Claudia, I will again interrupt when you approach 10 minutes before the end. Thank you.
Perfect, thank you. Okay, hello everybody. It's a pleasure to be part of this workshop for me, even though only virtually, unfortunately. And I wish I could be in Florence right now, but I have to teach at 1 today, so I cannot travel, unfortunately. But I would like to thank, nevertheless, the organizers for inviting me. And today I was asked to report on results of the best collaboration, mainly focusing on the Lattice QCD part, but also touching on the other topics. And I would like to point out before I start that recently the best collaboration has released the report of activities and overview of results, and it can be found on this publication. So just a motivation slide. What are the questions that we are trying to answer with finite density QCD? And here I have listed a few which we are trying to answer in the next few years. In particular, I would say the most prominent one, and the one that I am interested in the most at least, is whether we have a critical point on the phase diagram of strongly interacting matter. And this is a cartoon here of a compilation of experimental facilities and the regions of the phase diagram that they are supposed to explore. So I like this plot very much because it shows you, for example, the current range covered by Lattice QCD, and then how the experiments from different labs can come in and cover in patches the whole phase diagram pretty much. In particular, you can see that in this lower corner at low temperature and high densities, we have the new entry of neutron star emergers and signals from gravitational waves, which can help us to constrain these phases of matter. However, for example, one big question is whether matter created in low energy heavy ion collisions can reach even the deconfined phase, because we don't even know really where the phase transition line sits at large densities. So how to study high density matter in experiments on Earth? We mainly do it through heavy ion collisions by systematically decreasing the collision energy. And in particular, the most imminent results are from the RIC second beam energy scan, which finished its runs in 2021. And right now we are waiting to see the data. And soon we will have results covering all of these collision energies and all of these chemical potentials. And I also would like to mention that the study of dense matter will not stop after RIC. And here is a compilation of facilities where the study of critical point or onset of the confinement or dense hadronic matter or a combination of those will be pursued way after 2025. So you see that from the experimental point of view, there is a lot of going on. And so the theory needs to support the experimental program, and that is how the BEST collaboration was formed in the US. So BEST stands for Beam Energy Scan Theory Collaboration, and it is made up of 12 universities and 2 national labs. Here is the geographic distribution of them. And here I listed also what were the main goals of the BEST collaboration, which is to put constraints on the existence of a critical point in the QCD phase diagram, reach a new understanding of high density QCD, and also study chiral effects. In particular, more in detail, the idea is that if as a function of the beam energy, the path of a heavy ion collision in the phase diagram changes, for example, from passing through a first order coexistence line or going through a crossover regime, we expect to observe different signals in the data. And in particular, one that has been very much talked about is a non-monotonic behavior in various observables. And the most dramatic effect in particular is predicted to occur in fluctuation observables. And also additional evidence is probably provided by hydrodynamic effects on the lifetime and collective expansion of the fireball. And this would be controlled by the softening of the equation of state near a critical point. And also at the same time, if we have a chirally restored quark gluon plasma, then the handedness of fermions is conserved, but at the quantum level, these conservation laws are modified by triangle anomalies. And so in the presence of an external magnetic field, such as the one generated, for example, by the current of the colliding ions, these anomalies lead to novel transport effects, in particular the postulated chiral magnetic effect, which predicts charge separation induced by anomalous currents. So all of these effects, which we know they should be there, need to have a quantitative description so that we can recognize them when we see them in the data. And so the path to reach these goals is really to construct a solid theoretical framework to interpret these results from the second beam energy scanner trick. So I would say that to definitely claim or rule out the presence of a critical point or anomalous transport requires a comprehensive framework for modeling the features of heavy ion collisions at beam energy scan energies, which allows for a quantitative description of the data. So a crucial aspect of this effort, I would say, is to embed equilibrium quantities like the critical equation of state into also a dynamical scheme. And so this cartoon shows all these elements, which were the pillars on which the best collaboration was built. And this shows how they relate to each other. And in my talk, I will do my best to touch on all of them, but I will start from the upper right corner and spend quite some time on that, which is the Lattice QCD corner, which is my main interest within the collaboration. So from the point of view of Lattice QCD, the main goals within BEST were to obtain the most up-to-date prediction for the QCD transition line, equation of state, and fluctuations of conserved charges at finite density, as these are all relevant informations for the experimental and phenomenological modeling. So as you know, unfortunately, we cannot have first principle simulations at finite μb directly due to the Fermi sign problem. And this is why we actually don't know the phase diagram at high density. However, we have extrapolations or expansions that allow us to explore at least a limited portion of the phase diagram, some limited values of chemical potential. And this is what I will report on today. And the main driving forces in this effort within BEST were my group at U of H as part of the Wuppertal Budapest Houston collaboration, and also the BNL group as part of the Hot QCD collaboration. So both groups have recent results for the transition line of QCD, which can be parameterized as transition temperature as a function of μb in this way. So this is the typical way in which we parameterize the transition line. And you see that there are a few parameters in this transition line, like T0, which is the transition temperature at 0 chemical potential, and then kappa 2 and kappa 4, which are the curvature and fourth order coefficient of this expression here, and those are the quantities for which we can get information from the lattice. So because of the crossover nature of the transition, a definition of the transition temperature can be ambiguous. So a common choice is, for example, to locate the peak of the chiral susceptibility as a function of the temperature, and then by extrapolating this observable to finite chemical potential, it is possible to follow the location of the transition temperature with increasing μb. So the most recent and precise results for the transition temperature at μb equals 0, and then kappa 2 and kappa 4 are listed here, and they are from this paper from 2020. And here we have very similar results from Hot QCD collaboration that were contained in a paper just 1 year before. We also looked at the width of the chiral susceptibility and the height of the peak of the chiral susceptibility as indicators for the strength of the transition. Because the idea is that the chiral susceptibility is supposed to diverge at the critical point. So you can imagine that if we approach a critical point going to high mu b, then the width is supposed to become smaller and the height of the peak is supposed to become larger as we approach the critical point. So we found here, you see on the left, this is the width of the transition, and the width, as you see, up to 300 MeV in chemical potential does not change. And at the same time, the height of the peak does not change either. It stays pretty constant in the range of chemical potentials that we have studied. So I would say that from the lattice point of view, up to 300 MeV in chemical potential, we don't see any sign of approaching a critical point on the phase diagram. Then the next thing I want to report on is the equation of state. So the equation of state at finite density can be extracted, for example, as a Taylor expansion in powers of mu b over t. And these results are available from both collaborations, and both of them are limited to values of chemical potentials about equal to twice the temperature. And the two collaboration results nicely agree with each other. So as you can see, when you go to finite chemical potentials for the baryon number, you also need to make a choice also for the values for the strangeness and electric charge chemical potentials. So two very common choices in the literature, and both collaborations have results for both cases, are either to keep finite mu b, but mu s and mu q both equal to 0. Or the second choice is to go to finite mu b and at the same time go to finite mu s and mu q, and mu s and mu q are chosen to be functions of t and mu b that match the experimental constraints of having a 0 net strangeness and then net electric charge, which is 0.4 times the net baryon number, and these two reflect the conditions of the colliding nuclei. So in this plot, this is from Wuppertal Budapest, I show the basically the results for the Taylor expansion coefficient chi's, which are related to the C. The chi's are the C multiplied by 2n factorial. And these are plotted, you see chi2, chi4, and chi6 as functions of the temperature at 0 chemical potential, and this is the case of strangeness neutrality. So this would be the second case here for choice of electric charge and strangeness chemical potentials. And here you can see how some of the reconstructed observables look like from the Taylor expansion. These results are from hot QCD. And here you see on the left the pressure as a function of the temperature for different values of mu b over t. In the middle, you see the energy density, and on the right, you see the net baryon density. And you see that as we increase the ratio of mu b over t, some of the observables, in particular the net baryon density, show some wiggles, which we believe are not physical, but are the effect of truncating the Taylor series. So for this reason, our collaboration, Wuppertal Budapest, recently proposed a new expansion scheme which exploits the temperature and mu b dependence of the baryonic density and has a better convergent property compared to the Taylor series. So Jana will tell you all about this in detail in the next talk, so I don't want to go into detail here. I just want to mention that in this plot, you can see the scaled baryonic density as a function of the temperature, calculated at different values of imaginary chemical potential. And you see that all curves look very similar to each other. So if you rescale these different curves by t prime defined in this way, then they all fall on top of each other. And by exploiting this property, we define a new expansion scheme for the density, and from it we obtain all other thermodynamic quantities, and we can reach values of mu b over t with this new expansion scheme up to 3.5 now. And you see that the wiggles, for example, are well under control for this expansion scheme. And all details on this are contained in this paper. And like I said, Jana will talk about it in her talk right after mine. So another development within the best collaboration is an equation of state at finite independent mu b, mu s, and mu q. So as you know, in QCD, there are 3 conserved charges and therefore 3 chemical potentials. And in principle, you can define a generalized Taylor expansion where you expand in all 3 of them with these coefficients which contain diagonal and non-diagonal derivatives with respect to mu b, mu q, and mu s. So this is important as an equation of state because the conditions that I was mentioning before of net strangeness being equal to 0 and net electric charge being 0.4 times the net baryon number in the system are true only on a global level, but there can be local fluctuations in the fluid cells that hydro simulations are running where these values of mu s and mu q can be finite and completely random. And so for this reason, really it would be desirable to have an equation of state which gives you the possibility to independently change mu b, mu s, and mu q. And so we have within BEST actually separate efforts which have been looking at this. And in this plot, you can see, for example, some of these coefficients which have been parameterized by us in this paper, and completely equivalent results are also contained in this other equation of state by the BNL group. And in total, there are 22 of these coefficients if you want to stop at order mu to the fourth, so at order 4 in the expansion. And you can find all of them in this paper. And if you have them, you can reconstruct the whole thermodynamics at finite temperature, mu b, mu s, and mu q in a limited range of chemical potentials. So when it comes to the equation of state from the lattice, these are the main results. And so now I want to show you some results from both Lattice QCD collaborations about higher order fluctuations of conserved charges. So fluctuations are one of the most promising measurements from the MIM energy scan program, as they are sensitive to the presence of the critical point, and they allow also to compare first principle results to experiment. And you see here the skewness and kurtosis as functions of mu b, or as a function of collision energy, equivalently at RIC, with also experimental results superimposed. And you can see, for example, that Lattice QCD results are able to reproduce this decreasing trend in the kurtosis data with decreasing collision energy. So besides these efforts on which I reported, I would like to mention that there are several other results from Lattice QCD that have been calculated within the BEST collaboration. For example, fluctuations have been studied along the transition line, also in an effort to try to see whether any signature of the critical point could be seen. And analogously to what I already showed you for the peak height and width of the chiral susceptibility, also these fluctuation results show no sign of criticality up to chemical potentials equal to 250 to 300 MeV. Then there are efforts to study off-diagonal correlators, which also have been measured by the STAR collaboration. So it's important to have data from Lattice to compare to. And also we have results of fluctuations of baryon number up to 6th or even 8th order as functions of the temperature, and many more results. All of them are summarized in this paper that I mentioned at the beginning, and all of which are useful for the experimental program. So, however, this covers most of the first principle results that have been obtained within BEST, but I would like to point out that when you want to compare theory and experiment, several other effects may be important. For example, non-equilibrium effects, global charge conservation, proper treatment of particleization, effects of resonance decays, etc. And all of this motivates the non-lattice effort of a collaboration like BEST, where these effects can all be addressed. So to begin with the non-lattice part of the effort, I would like to start with the family of equations of state that within BEST was constructed to reproduce lattice QCD results, but also to contain a critical point in the 3D Ising model universality class, so that we can study its effect when we run hydro simulation with this equation of state. So what we did was we took the lattice QCD equation of state for the Taylor expansion developed by the lattice effort within the BEST collaboration, and we introduced a critical point on it in the 3D Ising model universality class. And then the hydro working group within the BEST collaboration has been testing this equation of state to see the effect of the critical point. Of course, the idea is that once data become available, we can run several simulations for different locations of the critical point and possibly have a constraint on the location and strength of the critical point when these data become available. And the community can benefit from this equation of state generating within BEST, because it's open source and it can be downloaded from this webpage of BEST repository. So the idea is that the Ising model has two variables, which are the reduced temperature, which we call R, and the magnetic field, which we call H here. And we can map those onto the QCD phase diagram by means of this mapping, which contains, if you want, 6 free parameters. So these parameters are the location of the critical points, so the critical temperature and baryonic chemical potential, the two angles that the Ising model axes form with the QCD ones, alpha 1 and alpha 2, and also W and rho, which basically tell us the relative scaling of the QCD axis with respect to the Ising model ones. So for the Ising model, the critical point is located at the origin of the axis, and the first order phase transition region corresponds to negative value of reduced temperature, and the crossover side is for positive values of reduced temperature. So that's why the axes are oriented this way on the phase diagram of QCD. And the idea is that these parameters are free, so one can play around with them to test, for example, how the size of the critical region influences the observables and how the location of the critical point influences the observables. So, however, these 6 free parameters, which seem like a lot, are not all of them are completely free, because we have, like I showed you at the beginning, some information from Lattice QCD on the transition temperature at mu b equals 0 and the curvature of the phase diagram. So using this information, we can relate, for example, T and mu b. So once you choose a location for the critical point in chemical potential, then the temperature comes for free because it has to sit on the transition line. And also we impose that one of the axes of the Ising model, the reduced temperature axis, is tangent to the phase diagram, to the phase transition line at the critical point. So that fixes the value of the parameter alpha 1 by imposing this. So at the end of the day, we only have 4 free parameters to play with, and everything I will show you in the following corresponds to this choice of the free parameters. But like I said, this is only one possible choice. And the idea is that many, many families can be generated, which and the people who play around with the code can play around with the parameters and test the effect of changing the parameters on the equation of state. So how do we proceed by merging the equation of state from Lattice to the one of Ising model? So the idea is that we assume that the Lattice QCD Taylor expansion coefficients are the sum of a non-Ising contribution and the singular Ising contribution, which comes from the critical point. And so by means of this equation, we are able to estimate effectively the non-Ising contribution. So the idea is that you have the lattice results for the coefficients, as I showed you at the beginning of my talk. You can calculate the Ising model one because we know the parameterized equation of state for Ising. And so by subtracting the Ising from lattice, you get a definition of the non-Ising coefficients. And this gives you this part here. So then the total pressure becomes the sum of the non-Ising Taylor expanded contribution up to order mu b to the 4th. That's where we choose to stop. And then the Ising part is then taken in full, and this brings the basically the contribution of the critical point into the game. So if you truncate this pressure up to order mu b to the 4th, this reproduces the Lattice QCD results by construction that I showed you before, but then by introducing the full Ising pressure, you can have critical effects due to the critical point. And so here, sorry, this is the pressure reconstructed in the temperature and chemical potential plane. And here you can see the critical point. And here are other thermodynamic quantities that you can reconstruct from the pressure. And here you can see, for example, the baryon number density, the second order baryon number susceptibility, and the speed of sound. And all of them are plotted as functions of T and mu b. And you see that, for example, for the baryon density, there is a discontinuity. For chemical potentials larger than the critical one, the baryon number susceptibility has a peak at the critical point, and the speed of sound as a dip at the critical point. Also, you can check the effect of the critical point on the isentropic trajectories, and you see that at low densities, they are not affected. And if I would superimpose here the Lattice QCD ones, they would be right on top of the ones from this equation of state. But then as you approach the critical point, you can see some structure forming that is due to this attraction of the critical point in these isentropic trajectories. One other thing that I would like to mention is that more recently, a second version of this equation of state, which is also available for download, can be has been obtained, which in the strangeness neutral case. So the only difference here is that instead of using the Taylor expansion coefficients corresponding to mu s and mu q equals 0, we're constructing a new strangeness neutral equation of state, which has the Taylor expansion coefficients corresponding to the experimental constraints of having 0 strangeness and net electric charge 0.4, the baryon number. And this equation of state is also available for download. So this equation of state has been used to study other things also within BEST, for example, the sign of the kurtosis, or also the critical bulk viscosity in these publications here. So moving on now onto other panels in this cartoon, let me start now from the hydrodynamic evolution and the initial conditions. So here are the scientific goals for this effort within BEST. So the point is that at the highest collision energies at RIC and even more at the LHC, the approach in nuclear are highly Lorentz contracted. So at the top Rick energy, the nuclei pass through one another in less than 0.15 Fermi over C, and at the LHC, the time is even shorter. Whereas at low collision energy, we need initial conditions for all three conserved charges, which have to take into account the fact that the nuclei are not so Lorentz contracted, and so there can be multiple scatterings between them because it takes up to 4 Fermi over C for nuclei to pass through one another. And then so this was one of the motivations for this effort within BEST. And then we also need a 3+1D viscous hydrocode, which is able to propagate all three conserved charges, taking into account their dissipative effects. So the initial conditions have been developed, which connect the pre-equilibrium stage of the system to hydrodynamics on a local collision by collision basis. So the idea is that the hydrodynamic evolution starts locally at a minimal thermalization time after the first nucleon-nucleon collision, and the sequential collisions between the nucleons also contribute as energy, momentum, and net baryon density sources to the hydro fields. So this figure shows that this approach can reproduce successfully the centrality and collision energy dependence of charged hadron pseudo rapidity distributions from 7.7 to 200 GeV. Also, so far, the hydro simulations have been extended to include the propagation of net baryon currents, including dissipative effects. And in this figure, you can see, for example, a plot by Chonshen and Bjorn Schenke, where they have extracted the fireball trajectory of a central gold-gold collision, shown here in the case of 19.6 GeV, but they have results for several collision energies. And also within the same working group, the effect of a critical point has also been tested. So you see here averaged fireball trajectories. The red ones correspond to the case of an equation of state, which is purely lattice QCD without critical point. And then you can see the effect on these trajectories, how they get slightly distorted by the critical point. So the black lines have been obtained by running the equation of state with critical point within the viscous hydro simulations developed within BEST. So moving on the dynamics of critical fluctuations. This is also something that needs to be addressed. So the idea is that in order to find critical point signatures in fluctuations, we need to develop a quantitative understanding of fluctuations near the critical point. And just studying them in Lattice QCD is not enough, because as the fireball approaches the critical point, also we need to study the evolution of the long wavelength fluctuations of the order parameter fields close to the critical point, which goes beyond a simple hydrodynamic description. So due to the critical slowing down in particular, long wavelength fluctuations fall out of equilibrium as the system approaches the critical point. And in addition, since the order parameter fluctuations themselves contribute to the stress energy tensor, their out of equilibrium dynamics back reacts onto the bulk evolution of the fireball. So this needs to be studied systematically, and two approaches have been followed within BEST: a stochastic approach with noise, and the deterministic approach in which correlation functions are treated as additional variables together with the hydrodynamic ones. The latter is called hydropras, and it is so far limited to the crossover side of the phase diagram and to 2-point functions, while we need, of course, higher point functions to study non-Gaussian fluctuations. But let us
10 minutes
see...
left.
Yes, thank you. So let's see the status of implementing these approaches into actual simulations. In the case of the stochastic method, we have two main results. The first one by the McGill group, basically in this approach, the stochastic hydro equations are solved using a momentum filter. And in the second effort, which is by the Nantes, Duke, and North Carolina state groups, net baryon fluctuations are studied by solving the fully stochastic diffusive equation in a finite size system with Gaussian white noise and using an Ising-like equation of state in 1+1 dimensions. And remarkably, in this case, the impact of critical slowing down has been observed. And finally, for the Hydro Plus, there are currently two main simulation results. The first one explores Hydro Plus in a minimum model with simplified geometry and equation of state to capture the interplay between critical fluctuations and hydrodynamics. And in particular, in this effort, they consider a radially and longitudinal expanding fluid, which is boost invariant and azimutally symmetric in the transverse plane and expands along the temperature axis at μb equals 0 with a hypothetically critical point, which is located so far just at small values of μb. And in the second set of study, we have the evolution of the two-point function of baryon density on top of a simplified QCD matter background known as Gabser flow. And this setup allows the authors to distinguish the main effects controlling the dynamics of long wavelength fluctuations and to explore systems with large baryon chemical potential in this case. So these figures here show the temperature profiles in the transverse plane for both studies. So moving on to the chiral magnetic effect. So the goals within the best collaborations were to model initial conditions, not only for the conserved charges that I discussed so far, but also for axial charges. And this has been done in the best collaborations by the Indiana group, which developed the code AVFD, which stands for anomalous viscous fluid dynamics. The second goal was to develop anomalous magnetohydrodynamics, and the first step in this direction has been the development of a code which calculates electromagnetic fields from the spectators and participant nucleons in relativistic heavy ion collisions. And this figure here shows the time evolution of the electric and magnetic fields. And then finally, we wanted to quantify the experimental signal of the chiral magnetic effect. And you know that there have been results from the isobaric run, which were announced last year by Richt, and they saw no sign of chiral magnetic effect. However, there is still the possibility maybe that conditions realized in experiment were not exactly the same conditions that theorists had predicted in order to clearly see the effect. And so this might call for more work to understand these high precision data from Richt. So finally, let me talk about the particleization at the end of the story. So the idea is that we need to then, after the hydro evolution, we need to develop the interface between the hydrodynamic part of the evolution and the hadronic transport such that it preserves fluctuation. So we've made all of this effort to study the critical fluctuations and how they evolved in hydro. So this information needs to be preserved at the moment where we turn the hydro cells into particles. And the traditional Cooper-Frye procedure matches only the averages of the conserved densities between the hydro and particle descriptions on the freeze-out hypersurface. So this is not enough, and progress in the best collaboration has been mainly in three areas in this effort. A microcanonical sampling algorithm that conserved all charges, energy, and momenta as given by hydro. And thus there has been an effort also on the particleization of Hydro Plus, that projects fluctuations from hydroplasts onto the final state hadrons. And finally, the development of a hadronic transport model with tunable potentials that allows you to study the effect of also criticality within hadronic transport. So to conclude my talk, the BEST collaboration has made tremendous strides towards developing a dynamical framework for a quantitative description of low energy heavy ion collisions. So the BEST framework is extremely modular, as I showed you this big cartoon with all the different pieces. Each component has been thoroughly tested and they are all related to each other. And so the idea is that we are now looking forward to the Beam Energy Scan 2 data so that we can perform potentially global Bayesian analysis within this framework and hopefully constrain our free parameters, including the location of the critical point and the strength of the critical region, which is really one of the main open questions on the phase diagram of QCD. And with this, I would like to thank you for your attention.
Thank you very much, Claudia. So we have question time. I see one from online, Fridtjof.
Yeah, Claudia, thank you for your nice talk. I guess I want to make a comment and maybe have a question also. I guess my comment, it's related to your slide 11.
Yes.
The wiggles.
The wiggles, yes.
I mentioned that at several occasions that these wiggles have nothing to do with anything that is related to convergence, but are most likely related to statistical effects. And this most likely is now gone, and it has been shown by us that it is a purely statistical effect. And this is published in our paper, which is now 1 month old. So looking at these Taylor expansions at 6th order, the behavior also in the pressure and number density is completely smooth when you have sufficient statistics. And you certainly cannot use this figure as an argument for discussing convergence of the Taylor series.
Okay, thanks for the comment. I wasn't aware of that, and these were results. These, if you want, were results within BEST, right? So I reported on those, but it's very good that you point this out. So, but one thing I would like to mention, I guess Jana will talk more about it in her talk, is also that similar wiggles arise when you truncate completely smooth sigmoid up to a certain order in Taylor. So maybe, I don't know up to which chemical potential now you can go, but I suspect that these wiggles will show up at some point if you don't,
they are not here, and they certainly have nothing to do with the radius of convergence.
No, the
discussing the radius of convergence is something different. So I will talk a bit about this on Wednesday, but I guess you are presumably still sleeping when I talk. So
I might try to wake up now that I know. Okay.
Maybe my question is related to your slide 21 when you introduce the equation of state. So you have there this, yeah, that's fine. You have there this particular parameter set which you used, but we know from other studies that a TC of 143 is presumably too high. The chiral transition temperature is probably below 130 MeV. And then when you make contact to cumulants in the region of 150 MeV, I wonder how you can possibly hope that these cumulants know anything about an icing critical behavior?
Yes, so two things. So this choice was made in the original paper, and it was before the chiral results in the chiral limit with the temperature of 132 MeV. So like I said, this is just one example. However, it is true that we are limited in our current version of the equation of state to chemical potentials smaller than 450 MeV. And this is exactly due to these wiggles in the Taylor that at least we cannot get rid of if we reconstruct, if we push this equation of state to higher values of mu b by just based on Taylor. So because of that, I had to put the critical point at 350, just not to put it on the edge here of the region where I can have my equation of state. But we are working now on implementing an easing plus a lattice equation of state based on the new expansion scheme, which hopefully will allow us to cover a bigger range of chemical potential, and that will allow us to finally bring the TC and mu BC to values which are more to your liking, I guess, so more in the region where we probably expect the critical point to be if it is there. I know that this is not a very realistic choice. Yes. And for the I guess your other comment for the Taylor coefficients, I agree with you that most likely when you calculate these coefficients at mu b equals 0, they will not have a big effect from the easy model. So again, this choice of parameters has an easy model contribution to them at mu b equals 0, which is relatively large. It's this blue curve here. However, you can choose other versions of the parameters, here in particular W and rho, which govern the behavior of these coefficients, such that their contribution at mu b equals 0 from the easing model would be completely negligible. And so if that's the case, then you could test that hypothesis as well. So the idea is to have a flexible equation of state where you can actually test this and have potentially contributions which are from critical point already at mu b equals 0 or not. And so that could be tested.
Okay, if we are quick, we can try to have two more questions. I've seen one by Jana. Günther?
Yes, thank you. I actually have a comment to Friedhoff's comment, and I will say a little bit about that in my talk. I think there is a slight misunderstanding about conversion, because no one is claiming that the radius of conversion is changed or anything. It's just that when you have the Chi-B6 at some temperatures negative and you go to high enough mu b, this will become dominant and you will see some kind of wiggle in your baryon density just from the cutoff. That does not mean that it won't converge if you had at higher orders. Not even that the conversion is necessarily worse than in the other regions, just that you see these behaviors which can be problematic if you ignore the arrows, because if you do a proper arrow on it, which of course you did for your baryon density, then it's not like your equation of state dips, you just see this larger arrow. So that's just, I think, the point. So nobody claims that it's not converging in that.
Well, I know many people who claim it from your collaboration. But aside from that, I guess your comment is irrelevant for the region we are looking at. As long as the Chi-6 is negative, which happens over a wide range of temperatures, at large mu b, these quantities will just go to minus infinity and will not have a wiggle. They can only wiggle in temperature in a region where Chi-6 starts becoming positive again.
Yeah, okay, sorry.
Yeah,
but I mean, it's related to this changes.
Jana, this is going off your own talk.
No, but okay, I will try to say it there. Sorry.
Sorry that we can't go for dinner tonight.
I agree with Jana because I heard the word radius of convergence from Fritjof, and I would like to reiterate that that's not what we mean. That's just nobody makes a claim on the radius of convergence here.
Okay, Anirban, can you be very quick?
Yeah, I didn't get one thing. You said the results for the independent chemical potentials, you show one result which you said is relevant for the heavy ion collision, given the fact that locally it could not be the situation that everywhere this is getting satisfied. But but given the fact there's all these quantum numbers you are talking about are the conserved numbers, so they can change locally also by diffusion only, and those diffusions are not actually independent. People have shown that. So how can I mean, for example, baryon diffusion will induce a strenuous diffusion. So
okay, but
yeah, so those are not independent. So I'm not sure what it means actually.
well, there are results where they model fluctuating initial condition in baryon number, electric charge, and strangeness, where they show that they fluctuate widely around the equilibrium values. And so that's what I meant. I don't know. I can send you the reference for that if you want.
All right, thank you. Let's thank Claudia once more.
Thank you.